A radio telescope peers 1,000,000 light years into space. A satellite relays communications between the continents. A space probe sends close-up pictures of the surface of the moon or the planets. A walk in space. A rendezvous high above the Earth at 18,000 miles per hour. Intricate electronic equipment helps make these things possible. As we expand our horizons, the need for extremely reliable electronic equipment becomes more urgent. Circuitry becomes increasingly complex, and space becomes more and more limited. Electronic computers require thousands of intricate circuits. Automated control equipment, extremely complex, but dependable, and in a small space. Communications and broadcast equipment is becoming much more compact. The consumer market has felt this trend, and so has electronic instrumentation. Complicated, high-performance instruments such as these have been made possible through the use of solid-state devices constructed on etched circuit boards. The circuit board enables an engineer to design equipment that is more reliable, more complex, in much less space. And for these reasons, Tektronix Incorporated, the world's largest manufacturer of laboratory cathode ray oscilloscopes, is relying heavily on the use of circuit boards in the design of new equipment. Because of the high component density offered by the use of these boards, it is possible to build more sophisticated instruments with greater versatility and reliability. Let's follow some of the techniques in the design and manufacture of high-quality circuit boards at Tektronix. This is where it begins, with the engineer's schematic diagram of the circuit to be built. A transparent ruled grid is placed on a light table. A piece of frosted drafting film is placed over the grid. Paper templates representing the components are aligned over this grid. Paths are determined for the interconnecting conductors. The templates are 4 times the size of the components they represent. The intersection of any lines indicates a possible hole position on the finished board. Solid lines indicate conductor paths on the top side. Dashed lines indicate conductors on the bottom of the board. Arrange and rearrange until you find the shortest path. Sometimes, where component placement is critical, it is not practical to make the layout directly from a schematic diagram. In such cases, the actual layout will be made and tried breadboard fashion. After this is working in a satisfactory manner, the component templates will be positioned and conduction paths laid out to duplicate those of the breadboard. When the layout is complete and all work has been checked against the schematic, the mock-up is made. Another grid is placed over the penciled layout. A frosted sheet of drafting film is placed over this grid. A black circle or pad is placed at each point where a hole is to be drilled in the board. Conductor paths are laid down with black opaque tape. And the top side of the board is done first. The black tape will duplicate each of the solid pencil lines. A separate 4x mock-up will be made for each side of the board. On the second side, the black tape will duplicate the dotted pencil lines. This larger size makes layout easier and assures greater accuracy. Slight errors in component placement will be reduced by 4 on the finished board. A final check is made between the mock-up and the original schematic. The mock-ups are placed on a copy camera to be photographically reduced. Now we have a photographic negative of the actual size of the finished board. Prototype boards may be handmade at this point to verify the design. And if everything checks okay, steps will be taken to make the circuit boards in production quantities. Film positives are made from the negative. They are carefully inspected. From these, silk screens will be made to be used in later operations. A silk screen actually contains no silk. It is a fine woven stainless steel or nylon mesh. All openings in the mesh are closed except where the conduction paths will be on the finished boards. Ink or chemical resistant material can be forced through the openings in the mesh. This is the electrochemical building. It was especially built to house all the electrochemical processes used to manufacture components for oscilloscopes at Tektronix. Manufacturing circuit boards is one of the major processes handled here. The fabrication of circuit boards begins. The raw material is a 13 by 20 inch sheet of glass epoxy, 1/16 inch thick, with a thin sheet of copper laminated on each side. We call this a flat. The material has been manufactured to very rigid specifications and was carefully inspected on arrival to assure that it is of the highest quality. Notches and registration holes required in the manufacturing process are punched into the flats. The first step is to drill all the holes. Now, this may be done in two different ways depending on the size of the production run. For smaller runs, it is done with a special drilling machine called a pantograph drill. The drilling template was prepared from the original mock-up. It is 2 times the size of the finished board. The pantograph drill has a reduction ratio of 2 to 1. At each point indicated on the template, a hole is drilled through 6 flats at a time. The high-speed drill is solid tungsten carbide. Each color on the template indicates a different drill size. Larger production of boards is best handled with a machine which is almost completely automated. Four heads, 16 drill spindles are controlled by numerical information on a punched tape. 10 flats, that's 2 stacks of 5 flats each, are drilled at one time. Several boards are produced on each flat. The number per flat depended on the size of the finished board. The tape not only programs the exact position of each hole, but it also determines which spindle or drill size will be used. The holes will be accurately positioned within plus or minus 0.02 of an inch. Although the drilling machine operates almost entirely without attention, the making of the programming tapes requires a great deal of operator skill. A microscope pinpoints the exact position of each hole on a photographic negative. This position is represented by a numerical code punched into the tape. This tape will be used to control the exact position of each hole drilled, as well as which drill spindle is used. All the component holes are drilled. Now we will deposit a metallic conductive path through the holes. The drilled flats are racked up, cleaned, and into an electroless copper bath. Here, a catalytic deposition of copper takes place. Now, this is not an electrolytic plating solution. However, a thin film, approximately 10 millionths of an inch, will be deposited out of solution to all surfaces, including the inside of the holes. Now, this was our objective, to place an initial deposit of copper in the holes to provide a conductive path for subsequent electroplating. The next step is to put a resistive material in the areas which are not to receive additional plating. Now, This is done by image screening. The screen, which in this case is stainless steel, was made photographically from film positives of the original circuit board mock-up. The resist now covers the entire surface of the flat except for the circuit paths. The flats will be dried and the opposite sides screened. It is necessary to know the number of square inches of surface to be plated in order that the proper plating current may be chosen. Light transmitted by the photographic positive and picked up by a photoelectric scanner gives an accurate indication of the area of the resist. A calculation will determine the current required. We can now plate additional copper on all surfaces not covered with the resist. Now, this operation is known as pattern plating. The back and forth motion forces the plating solution through the holes. Copper is plated on all the exposed conductor areas and through the drilled holes. Each hole becomes, essentially, a built-in eyelet. The flats are now ready to receive the final plating. In this case, gold, though other metals might be used. They are cleaned, then placed in an acid solution of gold salts. A few millionths of an inch of metal is deposited directly from the solution. This provides an initial non-porous deposit. The flats are rinsed and moved to the final plating tanks. Here, an electric current will deposit an additional, thicker layer of gold. Only the circuit areas are plated. The rest of the flat is covered with the resist. The final plate will protect the copper from oxidation and will also protect it from the etching solutions used later. The resist has served its purpose, so it can be removed now. We have the copper-covered glass epoxy base with additional copper and gold in the areas which will serve as conductors. This includes copper and gold through the holes. Now, we want to remove all the copper except that which is to serve as conductors. The etchant containing ferric chloride will dissolve copper, but it has no effect on gold. So the gold protects the underlayer of copper from the etching solutions. Metals other than gold might be used if they would resist the etch, protect the copper, and be readily soldered. We now have a flat of several circuit boards with gold-plated copper conductors. This plating extending through the holes, which will receive component leads. A scrubbing completely cleans the flats of any chemicals or residue left from the plating process. The metallurgical and process control laboratories are constantly checking the process. Before a new board goes into production, many tests are conducted. Each process must be kept completely in control at all times. Tests must be made on the thickness of the metal deposited, on the structure of the metal, to assure that the plating is of uniform thickness, that it is bonded properly to the layer below. Chemical tests, physical tests, electrical tests. A board is cut in sections. Here is the cross-section of the metal plated through a hole. This shows that there is an unbroken electrical path from one side to the other. The thickness of the final layer is measured on this machine. Beta particles are directed at the point to be checked. By measuring the reflections, or backscattered radiation, it is possible to accurately determine the thickness of the plate. From these measurements, the plating time and currents are verified and adjusted if necessary to assure the proper thickness and crystalline structure. Nomenclature is screened to the component side of the boards. A special solder mask is screened to the bottom of the board. This solder mask will prevent solder from adhering to any portion of the board except where it is desired. This makes it possible to solder the boards by the flow solder method. We will see this later in the assembly operation. The flats are sheared into individual boards. Boards are blanked out in a die. This punches out large holes, notches, or corners. They are routed to exact size. Square pins are inserted in many boards. These will be used for solderless interconnections in the final assembly. Test terminals and eyelets are added where required. Some of the plug-in boards require that special connectors be attached. This completes the manufacturing of the boards. Every board is given careful inspection. Hole size and positions are checked with an optical comparator. The boards are packaged, ready for component assembly. This is the assembly area. Here the circuit components are mounted on the boards. The component leads have been pre-cut and bent to the proper size and shape. Using sample boards as a guide, the components are inserted into the proper places. In the future, a machine may replace many of these hand operations. We are now ready to solder the components in place. This is an automatic soldering machine. The boards are in special carriers. Different carriers are used for each type of board. Nylon pins have been inserted in any holes which are not to receive solder. First, they pass over a foam flux unit. Then, over a hot plate to preheat them. Next, over 2 waves of molten solder. A pump keeps the hot solder flowing in this manner. The solder mask prevents solder from adhering to any points other than those that should be soldered. Capillary attraction and the force of the solder wave pulls the solder up through the holes. Here, we have an excellent electrical connection as well as a solid mechanical support for the component lead. Note the solder actually rising up through the holes, completely wetting the leads and bonding them to the plated copper conductors. Flux residue is removed by an ultrasonic cleaning process. The solder mask is not removed. It has no effect on the operation of the circuit, and it offers some protection to the surface of the boards. Here is a perfect board. Every connection properly soldered, and solder only on those places desired. Delicate components, which should not be subjected to the flow soldering or to ultrasonic vibrations and cleaning solvents, or parts that must be placed on the underside of the board, are now added and hand soldered. The boards receive a 100% visual inspection. Each board is tested under actual operating conditions. It is installed in the special test jig, which is actually part of an operating instrument. It is checked to see that it is operating properly and that all controls can be adjusted within proper range. The board is assembled into an instrument. The solderless connectors are attached to the square pins on the board. The oscilloscope is complete. It is adjusted and calibrated. These are precision electronic measuring instruments, cathode ray oscilloscopes. Instruments that are rugged and dependable. Complicated instruments, but easily serviced if necessary. Compact instruments with thousands of parts and connections. Instruments of higher performance, greater reliability, and smaller size. Instruments made possible through the use of modern etched circuit boards.